Hello there. In this video, we are going to discuss detailed solutions of all the questions those are appeared in GATE 2014 set 2 with respect to analog circuit. There are 4 sets of questions in GATE 2014, out of which we are in second set, and these are the question numbers you can find in GATE 2014 set 2 paper pertaining to analog circuit. We will discuss solution detail one by one. The first question is question number 11. In this question, an amplifier circuit is given with a transistor configuration. We have to find out what is the type of feedback used in this circuit. To find out the type of feedback or to know the key concept, you must refer to the GATE 2014, that is set 1. In question number 12, we have discussed few key points. Those are needed to find out the type of feedback for any type of circuit. Here we will apply those concepts to find out the type of feedback. We can redraw the circuit like this because this is grounded, so we have just connected these two terminals. So we have just connected these two terminals. Now we will see what is the type of sampling at the output and what is the type of mixing at the input. If we see at the output, the sampling, the voltage is taken here and the feedback is taken here. So that is happening at different point. If it is happening at different point, then the sampling will be of current type. Okay, so the sampling is happening at different point at the output, so it will be sampling will be of current type and the connection will be of series type. Similarly, if we go for the input, at the input the mixing is done in series with the input voltage, and if the mixing is series, then that is corresponds to voltage, so the mixing is done voltage mixing and the sampling is done current sampling. Okay, so we can name the feedback first output then input. So it can be current series or current voltage. So the feedback is of type current series or current voltage. So the feedback is current series or current voltage. If we see among the option, it is given as current series. So B is the correct answer. Thank you. Next question is question number 12. In this question, a differential amplifier circuit is given. We have to find out what is the dependence of this RE with respect to this SCM AD or common mode rejection ratio. Among the options, which one is correct? If RE is increasing, then what will be the effect on SCM AD common mode rejection ratio? Then accordingly we can choose the solution. If we can remember directly the formula, this is basically the circuit of a dual input and balanced output. Dual input means input is applied at both the input and output is taken from the difference of the both the output. Then that is called dual input and balanced output. The balanced output also can be called as a differential output, and in this case the common mode gain will be given by minus RC by RE plus 2RE. This is the formula. Similarly, we can approximate this because this 2RE value will be much more greater than this small RE. So we can write this expression minus RC by 2RE, and the differential gain is given by minus RC by RE. Okay, so if you see, the differential gain is independent of this RE resistance, whereas the common mode gain is dependent upon the RE and it is related as inverse of RE. So if RE is increasing, SCM will decrease. Okay. Now, if we try to derive this formula, we can easily derive this formula also. Here, suppose this circuit we can represent as V1 and V2, two inputs, that is V1 and V2 is applied, and the output is V01 and V02. Okay, so the difference voltage at the input is V1 minus V2, and the difference voltage at the output is V01 minus V02. So V1, V2, V01, V02, V1, V2, V01, V02 all are single-ended voltage. Okay, whereas this V0 and Vi, these two voltages are double-ended voltage or differential voltage. You can call them as differential voltage because they are representing difference of the voltage. So this is the circuit. We will now try to derive this expression for this SCM, that is common mode gain and differential gain. VCM is the voltage which is same point at both the input. The common mode voltage, as the name suggests, the common mode voltage, that is the voltage that component is same at both the input. Okay, and the VD is the differential voltage which is different at both the input. If we represent this V1 and V2 in terms of VCM and VD, we can represent like this, or we can find out the common mode voltage as the average of both the voltage, that is V1 and V2, and VD as the difference of V1 minus V2. So we can represent these voltages V1 and V2 in terms of VCM and VD, and we can redraw the circuit like this. Okay, so this is the VCM, that is the common mode voltage for both the input, and these are the two different voltages, that is this is out of phase with this VD by 2. Okay, so this is the circuit we have. So this is the circuit we have in terms of common mode voltage and differential voltage at the input. Similarly, at the output also we can have common mode output as well as differential output voltage. So suppose VOC and VOD are the common mode voltage and differential voltage at the output, then we can represent this as V01 and V02 in terms of this common mode voltage and differential voltage like this. Similar way, VOC is the average of both the output voltage, and VOD is the difference of voltage, single-ended voltage at these two terminals. So let us try to find out what is the common mode voltage. For common mode voltage, the input will be the common mode voltage, that is the VCM. Okay, VD will be removed, so VCM is the voltage, and at the output the voltage will be same, that is at both the terminals. So these two terminals will be shorted, and VOC is the voltage at the output. So the gain is nothing but VOC by VCM, that will give us the gain of the amplifier, and that will represent the common mode gain. At the output, VOC is nothing but the average of these two voltages, as both are sorted, so both are same potential. So both will give same potential at the output. So if we represent the small signal circuit of this part, that is one side, then we can represent VCM, and we can have a current dependent current source. Beta RE is the internal input impedance of this transistor. Okay, and V01 is the voltage at this point, that is the output voltage at this point. And similarly, this part also we can represent like this. Okay, now about this part, this for small signal circuit, all the current sources and voltage sources will be represented by their internal resistance. So we will assume this voltage source, DC voltage source, and current source will be ideal. So the voltage source will be represented by 0 internal resistance, and the current source will be represented by infinite resistance. So we will have this RE directly grounded, and that will be connected to both sides. So we can have one RE here, that will be connected to both the part. So this represents the complete small signal circuit when VCM voltage, that is the common mode voltage, is applied at both the input. So we have this circuit, and V01 or V02 both are equal, and that will represent the output voltage, that is common mode output voltage. Okay, so the common mode output voltage is nothing but V01, we can write V01 is same as the common mode output voltage. V01 we can write beta IB into RC. Okay, and beta IB will be flowing in upward direction, so it will have a negative sign, that is minus beta IB into RC. Now we will try to find out what is IB in terms of VCM. For that we have to apply KVL across this loop. Suppose I dash is the current that is flowing through this branch. I dash is nothing but IB plus beta IB, that will give us beta plus 1 IB. Okay, beta plus 1 IB. Again, let us, the current flowing through the RE resistor is IE. The IE value will be I dash plus IB plus beta IB. Okay, so that will give us 2 times beta plus 1 IB. So IE value is nothing but 2 times beta plus 1 IB. Now let us apply KVL across this loop. So VCM value will be equal to IB into beta RE plus whatever the IE current is nothing but 2 times beta plus 1 IB into RE. Okay, so VCM value will be like this. We can represent IB in terms of VCM. So IB is equal to VCM by beta RE plus 2 times beta plus 1 RE. Now this IB we can substitute here. Okay, so V output C, which is equal to V01, is equal to minus beta RC divided by beta RE plus 2 times beta plus 1 RE into VCM. So the common mode voltage gain is nothing but VOC by VCM, which you will get like this, assuming beta value to be very large, so that beta plus 1 is same as beta. So we have minus RC by RE plus 2 RE. That is the common mode voltage gain. And if we can approximate this, that is 2 RE is much greater than this small RE. So the common mode voltage gain will be minus RC by 2 RE. Now let us try to find out what is the differential voltage gain. For differential voltage gain, this will be 0. Only Vd by 2 will be applied. Okay, so we will have this circuit. Differential voltage gain is nothing but VOD by Vd. VOD at the VOD is nothing but V01 minus V02. That is the difference of these two voltages. Okay. Now if you represent the small signal circuit, the circuit will be looking like this. Here one point you have to note, as this voltage is of opposite sign of this one, so the output voltage will have positive voltage, and hence the current source here, the current dependent current source will be of opposite sign. Okay, so accordingly we will try to find out what is the voltage gain AD. So this is the small signal circuit. VOD is nothing but difference of the two output voltages. V01 is nothing but beta times IB into RC. Okay, beta times IB into RC, and there will be negative sign, whereas V02 there won't be any negative sign, beta IB into RC. So the VOD is nothing but minus 2 times beta IB into RC. Now we will try to find out this IB in terms of Vd by 2. So if we see I dash is same, that is IB plus beta IB, that will give us beta plus 1 IB. Now if we apply KCL at this node, suppose I is the current flowing through this branch. If we apply KCL at this node, this current is entering and these two current are leaving, so the I current will become 0. That is, there won't be any current through this RE. Okay, so if we apply KVL, across this loop, we can write Vd by 2 is simply IB times beta RE. As there is no current flowing through RE, so this IARE will be 0. So Vd by 2 is equal to IB into beta RE. So IB expression is Vd by 2 beta RE. We will replace this IB here. So VOD will have this expression. Finally, we will have differential gain as minus RC by RE. So we have common mode gain minus RC by 2 RE, whereas differential gain minus RC by RE. CMRR is nothing but differential gain by common mode gain, which is equal to 2 RE by RE. So if we see the dependence of RE on all these three values, here the RE is inversely proportional to the common mode gain, and here the RE is directly proportional to the CMRR, whereas the differential voltage gain is independent of RE. Here in the question it is given this RE is increasing. This RE is increasing. If this RE is increasing, CMRR is increasing and ACM is decreasing. But here ACM is increasing, so A is not the answer. AD is increasing is given. AD is independent of RE, so C is also not the answer. Common mode rejection ratio is increasing because it is directly related to RE. So CMRR also increase as RE increase. So common mode rejection ratio will increase, not decrease. Hence B is the correct answer. Thank you. Next question is question number 13. In this question, two amplifiers are cascaded. We have to find out what is the overall voltage gain of this configuration, and their parameters are given here. We have to find out what is the overall voltage gain. So we can represent each amplifier as a voltage dependent voltage source. So voltage dependent voltage source, we can represent voltage dependent voltage source like this, and there will be input impedance and output impedance like this. Similarly, A2 can be cascaded to this, A2 is cascaded, and finally this RL will be connected at the output. RL is connected at the output. We have to find out what is the voltage gain, that is V0 by Vin. So we have this circuit basically. This is the overall circuit, and these are the parameters. Those are given in the questions. We have to find out what is the V output by V in. We can express this V01 in terms of this voltage, that is voltage dependent voltage source. V01 is nothing but V into, okay, V into is nothing but the voltage across this. So we can apply voltage division rule to find out what is the voltage across this. So as I said, V01 is nothing but V into. After applying voltage division rule, the voltage across this is nothing but AV1 V in into R into divided by R01 plus R into. Similarly, we can find out what is the output voltage across this RL in terms of this voltage. So V output is nothing but AV2 V into RL divided by R02 plus RL. Now this V into expression, we have this V into expression, we will replace this V into here. So we will have the output voltage like this. Hence we can find out the gain as V0 by V in, that will give us this expression. Every value in this expression is given. AV1 is nothing but 10, AV2 is nothing but 5, Rin1 is not needed, Rin2 value is 5 kilo ohm, R01 value is also given, that is 1 kilo ohm, and R02 value is 200 ohm. So we will substitute all these values to find out the voltage gain, and the voltage gain will be coming out 34.722, that is the voltage. So the approximate overall voltage gain is 34.722. Thank you. Next question is question number 37. In this question, a circuit is given with diode, resistor and voltage source. Here the input voltage is applied a sinusoidal voltage of magnitude 5 volt, and the on voltage of the diode is given to be 0.7 volt. We have to find out what is the minimum and maximum value of the voltage at the output. Okay, we will see when the diode is on what is the voltage, and when the diode is off what is the voltage. First, when the diode is on, one current I will be flowing through the circuit. So let I is the current that is flowing through the circuit. Then we can apply KVL to find out what is the output voltage. The output voltage is equal to I into R2 0.7 plus 2. So for the output voltage to be maximum, this current to be maximum, and for this current to be maximum, that is this current to be maximum, the supply voltage has to be maximum, and the maximum value of the supply voltage can be 5 volt. Okay, so the maximum voltage of the supply voltage can be 5 volt. So during 5 volt, what is the current? That current will be the maximum current. We will try to find out that current. So the maximum current is nothing but 5 minus 2.7 divided by the resistance, total resistance, that is 2. That is 1 plus 1 equal to 2 kilo ohm. So that current will give us 1.15 milliampere. That is the maximum current. Now this current, if we substitute here, that will give us the maximum output voltage. So the maximum output voltage is nothing but this current is substituted here. So after substituting this, we will get the maximum output voltage to be 3.85 volt. Now let us consider the other case, that is when the diode is in off state. So when the diode will be in off state exactly? The diode will be in off state when the input voltage is ranging between 2.7 volt to -5 volt. That is, it is less than 2.7 volt and it is greater than -5 volt, because it cannot be go less than this, because -5 volt is the minimum voltage. So during this voltage span, the diode will be in off state. As the diode will be in off state, there won't be any current. So whatever the input voltage, that will be directly appear at the output voltage. So we can replace this Vi with Vo. So Vo will have span of 2.7 volt to -5 volt. So the minimum value of the V output can be -5 volt. From this limit, the minimum value we can find out to be -5 volt. Hence, the minimum value can be -5 volt and the maximum value can be 3.85 volt. So among the option, if you see, option C is the correct answer. Thank you. Next question is question number 38. In this question, an NMOS transistor is given, okay, and the threshold voltage of the transistor is given, and it is given. You have to neglect the channel length modulation, okay, and it is given. In the question, it is given for drain voltage 1.6 volt, the ID current is 0.5 milliampere, and somehow if the VD is adjusted to 2 volt, that is by changing the value of R and the supply voltage VDD, then what is the new ID current in that case? So if you see in the circuit, as gate and drain are shorted, this transistor will be always in saturation region. Okay. Now what are the things given? Threshold voltage for the transistor is given 0.8 volt. VD1 is 1.6 volt. For that, the ID1 current is 0.5 milliampere. 0.5 milliampere. If the drain voltage changes to 2 volt, then what is the new ID current? That we have to find out. So here if you see, this VD is same as VG and same as VGS, because VS is 0. Okay. Now we can write the saturation current equation. ID1 is equal to Kn by 2 VGS1 minus VDH square. Similarly, ID2 current will be in terms of VGS2 like this. We can divide these two current. So we will get this expression. Kn by 2 will be cancelled. Now VGS2 is nothing but VD2. Okay. Similarly, VGS1 is nothing but, according to this expression, VGS1 is nothing but VD1. Okay. We have given with all this value, and ID1 also we know. We have to find out this ID2. So by putting all this value, we will get this ID2 is equal to ID1 into 2.25 times, and ID1 is given 0.5 milliampere. So we will get ID2 as 1.125 milliampere. If we say among the option C is the correct answer. Thank you. Next question is question number 39. In this question, one NMOS transistor and one PMOS transistor is in series, basically a CMOS circuit, and it is biased with two resistors, that is R1 and R2, which have equal value 10K. The K value for both the transistor is same, and the magnitude of the threshold voltage for both the transistor is also given to be 2 volt. We have to find out what is the ID current, that is the drain current for this circuit. Okay. Now we can turn the voltage at this node as VGL and this node as VGP. So first of all, before solving this type of problem, first of all we have to find out the region of operation of these two transistors, that is NMOS transistor and PMOS transistor. We have discussed previously during GATE 2009 question number 57 and 58 analysis, how to find out the region of operation of NMOS and PMOS transistor when they are connected in series, or when ID is same for both the transistor. We have to find out which transistor is overdriven, that is VON. VON we have to find out from both the transistor, that is VON is equal to VGSN minus VTN. Similarly for PMOS, VGSP minus VTP. Now we have to find out if both the voltages are equal, that is VON is equal to VOP, then both will be in saturation region. Otherwise, the higher voltage means the corresponding transistor will be in linear region. So here it is a higher voltage, so NMOS will be in linear region and the other transistor will be in saturation region, and vice versa. So the conclusion is overdriven transistor will be in the linear region. So here we will try to find out VOP and VON. Here VOP is equal to VGSP minus VTP. VGSP is nothing but VGP minus VSP. Okay, VGP is nothing but, we can apply voltage division rule here. 12 volt into 10 by 10 plus 10, that will give us 6 minus 12, because VDD is nothing but VSP for this PMOS transistor. So that will give us minus 6 volt. So VOP is equal to minus 6, minus VT for PMOS transistor is negative, so minus 2. So VOP is minus 4 volt. Now we will try to find out what is the VON. VON is nothing but VGSN minus VTN. VGSN is nothing but, this is 0 minus 5, this is 0 minus minus 5, that is 5 volt. Okay, VGSN is nothing but VGN minus VSN, VGN minus VSN minus VTN. So if we put this value, that is VGSN is equal to 5 volt minus threshold voltage of this transistor is 2, so that will give us 3 volt. So VON is equal to 3 volt. If we see, the VOP magnitude is greater than VON, so the PMOS is in overdriven state, so that will be in linear region and NMOS will be in saturation region. Here in the circuit, we have to find out what is the ID current. We can easily find out the ID current by applying the saturation equation for NMOS transistor. So here this PMOS transistor is in linear region and NMOS is in saturation region. So we will apply the saturation current equation. That will be ID equal to Kn by 2 VGSN minus VTN square. VGSN is equal to 5 volt, VT is equal to 2 volt. We will substitute these two. Along with that, K value is also given 0.5. So we will get the drain current ID is equal to 0.9 milliampere. So that's the answer of question number 39. This concludes analysis of all the questions those were appeared in GATE 2014 set 2. If any questions are missing, please let me know so that those questions can be added in this part. If you have any query or suggestion, you can freely ask. I will be happy to address your queries. See you in the next lecture. Until then, stay safe, stay healthy, and most importantly, keep preparing harder and harder.